When we cannot evaluate an improper integral directly, we try to determine whether it converges or diverges. The principal tests for convergence or divergence of improper integrals are direct comparison test, limit comparison test, p-test, and q-test. We start from direct comparison test for type 1 improper integral. What is type 1 improper integral? If you have infinity at least in one of the boundaries of integration, in this case, the improper integral is called type 1 improper integral. Now look at these inequalities. The function f is greater than g, and they are all positive functions on the interval a infinity. Okay, be careful about these inequalities. If improper integral of f converges, then improper integral of g must be convergent. Okay, so what does it mean? Assume that we have a known integral, and assume that we have a question, we have an improper integral in the question. It is requested to find. Okay, so and we want to compare these two improper integrals, but we know the convergence of this one, right hand side, the greater one, and we know that the greater one is a number, not infinity. Okay, we can calculate a known improper integral, and we know that the answer of this is a number, not infinity. So if the greater one, if the answer of greater one is a number, then the answer of smaller one must be a number. The answer of smaller one cannot be infinity. Okay, so this is why the smaller one must be convergent improper integral. So we compare two improper integrals. This is why it's called comparison test. Let's look at the second case. Again, considering all these inequalities, if the improper integral of g diverges, then improper integral of f must be divergent. Again, we have a known improper integral. We know the convergence of this, and we have an improper integral in the question. It is requested to find. Now, assume that the answer of smaller one, this is a smaller one, right? In this case, the answer of smaller one is infinity, not a number. Okay? If the answer of smaller one is infinity, what can we say about the answer of greater one? Okay. If the answer of smaller one is infinity, not a number, the answer of greater one must be infinity, cannot be a number. Okay. This is one. If the improper integral of g diverges, then improper integral of f must diverge. Okay. Now let's try to understand this test, comparison test for type 1 by some examples. And the first example is integral from 1 to infinity. Since we have infinity here, this is type 1 improper integral. And we will compare the integrand with some other function. We know that cosine function, actually, cosine x is in between -1 and 1, right? But cosine square is in between 0 and 1. We cannot have minus values for cosine square. If you divide each term by x squared, then you get the integrand of the question. Okay. Now we can compare these two functions. 1 over x squared is greater than cosine square x over x squared. So what can you say about integral from 1 to infinity dx over x squared? Do we have an idea about this improper integral? Yes, we have. We can compute this improper integral, and we know that the answer of this is a number. So this is a convergent improper integral. Now, if the greater one, if the answer of greater improper integral is a number, then we can say that the answer of smaller improper integral must be a number. So by direct comparison test, the given improper integral is convergent. This is the answer. Okay. So what about the second question? I want to compare the integrand with some other function. We know that for x is greater or equal than 1, x plus x cube is greater than x cube. Okay. So if you take square root of each size, you have square root of x plus x cube is greater than square root of x cube. If you reverse this inequality, you have 1 over square root of x plus x cube is smaller than, since you reverse, 1 over square root of x cube. Okay, we have this inequality. And we know that this is very important. Integral from 1 to infinity dx over x to the power 3 over 2 is a convergent improper integral, since the power of p, which is 3 over 2, is greater than 1. Okay, using the p-test, we know that this is a convergent improper integral. If the answer of greater one is a number, if the greater one is a convergent improper integral, we know that the smaller one must be a convergent improper integral too. So the given improper integral is a convergent improper integral. Let's look at the third problem. This is type 1 improper integral, since the boundaries of integration from a number to infinity. And we know that when x is greater than or equal to 2, ln function is less than x. ln x is less than x. Using this inequality, if you reverse this inequality, you have 1 over x is smaller than 1 over ln x. And we know that the improper integral from 2 to infinity dx over x. What can we say about this improper integral? We know that this is a divergent improper integral, since p is 1. Okay, since p is 1, it is a divergent improper integral. Again, if the smaller one is a divergent improper integral, the greater one must be divergent. If the answer of smaller one is infinity, the answer of greater one must be infinity. This is why the given improper integral is divergent improper integral. Let's look at the second type test, limit comparison test. Limit comparison test for type 1. Assume that f and g are continuous positive functions on the interval a infinity. We are still working on type 1 improper integrals. And assume that the answer of this limit of f over g is equal to L. So what is L? We have three cases. In the first case, we assume that L is a positive finite number. So it cannot be infinity. It must be a number, positive number. Okay. If you have this case, if L is a positive number, in this case, if improper integral of g converges, then improper integral of f also converges. Or if improper integral of g diverges, improper integral of f must diverge. Okay, we have two cases. So what do we understand from the first case? Assume that L is a finite positive number. In this case, the convergence of improper integrals of g and f is the same. So they have the same convergence types. Both of them converge or both of them diverge. In the second case, if the answer of this limit is equal to 0 and improper integral of g converges, then we say that improper integral of f, which is requested to find, also converges. In the third case, if the answer of this limit is equal to infinity and improper integral of g diverge. In this case, improper integral of f, which is requested to find in the question, must diverge. Okay? We have three cases. So let's try to understand this test by some examples. Investigate the convergence of the following integrals. We see that they are type 1 improper integrals. Let's first write the function f. We now solve the first question. F of x is equal to the integrand 1 over 2 to the power x, x plus 1. This is f. So we have to choose a g function. Okay, we choose this function, and in the next step we will find the limit of f over g, and we will examine this limit according to the answer of this limit. So we'll use the limit comparison test and say something about the convergence of this improper integral. So it is all up to us to choose g. Okay, let me choose g as 1 over x squared. So in this case, limit of f over g is equal to limit of x squared divided by, if you substitute, you have x squared over 2 to the power x times x plus 1. When x tends to infinity, as you see, you have infinity over infinity case. So we have to apply L'Hopital's rule. Let's apply L'Hopital's rule. If you apply once, then you have derivative of x squared is 2x, and derivative of denominator is equal to the parentheses of 2x. You have x plus 1 ln 2 using the properties of derivative of exponential function, and finally you have 2 to the power x. As you see, you have the multiplication of two functions. When x tends to infinity, you still have infinity over infinity. So we have to apply L'Hopital's rule again. So if you apply again, you have 2 in numerator, and you have very complicated function in denominator. The parentheses of 2 to the power x ln squared 2 x plus 1 and 2 ln 2. Okay. When x tends to infinity, the answer of this is equal to 0. So as you see, L, which is L, this is L, right? L is 0. L is 0. Let's look at the cases. We had the second case. L is 0. If this improper integral of g converges, then we can say something about the question. So what about the improper integral of dx over x squared? Does it converge or diverge? It converges since p is equal to 2 is greater than 1. So this is a convergent improper integral, and L is equal to 0 using or let's say by a limit comparison test. The given improper integral also converges. This is done. Let's look at the second question. Let's first apply direct comparison test to this question. Okay, let's first try this one. We know that e to the power minus x is greater than 0 and less than 1. Okay, so when x is greater than 1. If you substitute this expression, you can also say that, you don't have to substitute actually, you can also say that 1 minus e to the power x is also in this interval, right? If you divide each term by x, then you have this inequality. So we know that integral from 0 to infinity dx over x diverges. Okay, this is a divergent improper integral. So if you use direct comparison test, you cannot say anything about the given improper integral. Why? The greater one diverges. What can you say about the smaller one? It can be anything. It can be divergent. It can be convergent. The answer of this can be infinity or a number. This is why direct comparison test does not work. So I want to apply, for this reason, I want to use limit comparison test. So in order to use limit comparison test, I choose a function of g. Let's say g is equal to 1 over x. Since we have x in denominator, I choose 1 over x. And f is also given in the question. This is 1 minus e to the power minus x over x. So what is the limit of f over g? Limit f over g when x tends to infinity is equal to limit x tends to infinity f over g 1 minus e to the power minus x divided by x over 1 over x. This is f over g. You can simplify this axis and finally you have this limit expression is equal to limit x tends to infinity 1 minus e to the power x. So when x tends to infinity, this part tends to 0 and the answer is equal to 1. The answer of this limit is equal to 1. Let's look at the cases again. If L is 1, so what does it mean? We have the first case. So the convergence types of improper integral of f and g is the same. They both converge or they both diverge. So what can you say? What do we know about the integral of what do we know about the integral of g, improper integral of g? Integral from 1 to infinity dx over x. This is the improper integral of g. We know that this is a divergent improper integral. Okay? So the convergence of this improper integral and the given improper integral is the same by limit comparison test. So this is divergent by limit comparison test since L is equal to 0 and improper integral of g diverges. This is all. We have a second type of limit comparison test for type 1 improper integrals. This is also called p-test. Okay, and we actually take x to the power minus p for g function. Then limit f of g becomes limit of x to the power p times f when x tends to infinity. And we examine the answer of this limit. Let's say this is equal to L. If L is a bounded positive number and if p is greater than 1, in this case, the given improper integral converges. If L is infinity or a bounded number, again, greater than 0, and if p is less than or equal to 1, then the given improper integral, in this case, diverges. Let's try to understand this problem with an example. Determine whether the following integral converges or diverges. Let me first write down f. F is 1 over square root of 1 plus x to the power 6. Since we have x to the power 6 in denominator, let's choose g of x as x cube. Okay. In this case, so let's say p is equal to 3. Okay. So I will manipulate the limit expression. I rewrite the limit for this problem. When x tends to infinity, limit of f over g. In this case, we don't write f over g. We write x to the power 3, x cubed, times g, which is 1 over square root of x to the power 6 plus 1. Okay, and this is equal to limit when x tends to infinity, square root of x to the power 6, so you can take this expression into a square root function. In this case, you have x to the power 6 over x to the power 6 plus 1. So if you take the limit to the inside of square root function, you see that the answer of this limit is equal to 1. So L is equal to 1, P is equal to 3. Let's look at the conditions of this expression. L is a number and P is greater than 1. In this case, by p-test or modified limit comparison test, the given improper integral converges. Okay, this is all.